Okay, so last one because I cut a different one out, which is good because it was terrible. We looked at before at a confidence interval, and in that we had given information. We had the population standard deviation, sample size, sample average, and we looked up a number in the table based on how confident we wanted our interval to be. So we could use those bottom numbers when we had a population standard deviation. This is where those slight differences come into play. Normally, we don't. Normally, we don't have a population standard deviation. We usually have a sample average, and from that, we usually have a sample standard deviation. So because we have a sample information, our interval, we have to have a little bit more fudge room. We're inferring data of a sample to a larger population. So this is where we have what's called degrees of freedom come in, okay? So in our table F, if we are given a confidence interval, the 80, so on and so forth, we use those numbers at the bottom, where that Z number is, okay? But if we have a sample standard deviation, we have to use our degrees of freedom, and then we're going to go over to whatever correlating confidence level we want. So in order to find that, the degrees of freedom is always n minus 1. So whatever our sample size was, we're going to take one less than that. We go to this column, and then we go over to whatever level they tell us. So if they say 90%, we would go and look at the 90% column, okay? And that's the number we use. Rather than a Z score value, we have what's called a T score. Why, I don't know, but they label it what they do. Okay, so here I used to have a picture, but I think I explained it already. Okay. Other than getting a different value for this, everything else is exactly the same. This is still the standard deviation. This is still the sample size, the n. This is still the sample average. And this now is still from table F. But we need to find the degrees of freedom. Okay. So we're going to use this example. It says a random sample of 10 children found that their average growth for the first year was 9.8 inches. So they told us a sample of 10 children, their average growth is 9.8. So they tell us that the average is 9.8. Assume the blah, 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 and the sample standard deviation is 0.96. Again, they said there's 10 children. So our degrees of freedom is n minus 1. So in this case, if n is 10, our degrees of freedom will be 9. Okay. And it wants us to find the 95% confidence interval for the population mean. Okay, so we're going to look at table F, and tells us we want to be 95%. So here's 95%. And rather than going all the way down, now we're going to have to use this degrees of freedom column to know where to stop. So our degrees of freedom was 9. So here we are at 9. And then we go over to 95%. And we're going to use this value, 2.6, back it up, 2.262. For whatever reason, I can never say that correctly the first time. 2.262. Okay. So we're going to use these values and do just like we did before. We find the margin of error, we subtract it from the mean to get the low end, we just add it to the mean to get the high end. Here, it's asking us, well, what are the keywords in this problem that tell us that we have to do the degrees of freedom rather than just look at the numbers at the bottom? And the keywords are sample, standard, deviation. Okay, this all together. Not just standard deviation, not just sample, but the fact that the standard deviation is from a sample tells us that we have to do that. All right, so let's rock and roll with this. We're gonna have 9.8. Two. Again, we're gonna get this value first. That's the margin of error. 0.96 divided by the square root of 10. 2.262. And let's say 0.69. So that's the margin of error. We're going to subtract it. And then we add it. 9.8 minus that. Okay. So here, when we finish out the statement, we can say one can be 95% confident that the population mean of the first year growth is between this and 10.49 inches. Okay. The low number always comes first, the big number always comes second because the interval is low to high, right? Start to stop. Okay, let's do one more since it's so much fun, right? Here it says a sample of 14 randomly selected commuters in Chicago showed that the average of the commuting times was 33.2 minutes. I think that's very low. The sample standard deviation was 8.3. Find the 99% confidence interval of the true mean. All right, because that's all we need to know. In a random order. So it says a sample of 14 randomly selected commuters, so n is 14, that the average commuting times, sorry, that's back, average commuting times was 33.2. Wow. And the sample standard deviation was 8.3. So well, you're going to have to use degrees of freedom and that t-score value because we have a sample standard deviation. So degrees of freedom is n minus 1. So 14 minus 1 gets us 13. So we're going to look up in the table at 13 in this column. And it says we want to be 99% confident. So we're going to go all the way over to here, 0.012. 3.012. And my cat is rubbing himself all over the laptop again. Okay. So in the formula, we find the margin of error first. And okay, cat is only slightly in the way now. So we're going to find this value. And a lot of times you want to be careful because after we get degrees of freedom, sometimes we accidentally put that in for n value down here. So just be careful you're putting in the actual n value. So here we have our margin of error is 6.68, so we're going to subtract it and then add it to our average. And so here, based on our information, we can be 99% confident that the true average of commuting time for Chicago commuters is between 26.5 minutes to 39.88 minutes. So the average is somewhere in between these two times. Okay? I'm thinking it's a lot more than that too, just because I know how bad it could be in Chicago. All right, so hopefully you are able to follow along and not see so much of my cat's butt in the camera. And yeah, so let me know if you have any problems. See you later.